Hey everybody, welcome back to EM378SI Online. We're starting our third session of the week, so let's get into it. So in this problem, we have a model submarine 1/15th scale is to be tested at 180 feet per second in a wind tunnel with standard sea level air, while the prototype will be operated in seawater. Determine the speed of the prototype to ensure Reynolds number similarity. So the gist of this problem is that we have this big submarine we're building, but to be able to test it, they're building a smaller scale model, 1/15 scale, and their wind tunnel they're going to be running at 180 feet per second. But we want to make sure that the test we're running and how fast the prototype has to be, how fast the model has to be moving. We got to make sure those match up so that the model is accurate to the actual prototype. And they're asking for Reynolds number similarity, and the Reynolds number can be represented either as velocity length over nu, which is your kinematic viscosity, or it can be density velocity length over kinematic viscosity, or dynamic viscosity. Either one. We'll be using this first one here. You'll see this one later in the class more often. So I'm going to call the model is going to have the is going to have a little m at the bottom is how I'm going to notate that. And the prototype similarly is just going to be parentheses p. And what we need is for the Reynolds number of the model to be the same as the Reynolds number for the prototype. And the ratio that we have is 1/15 scale. This relates to what would be the length here, right? So we know that the length of the model is 1/15th the length of the prototype. And we'll use this relationship to solve for what we need. So Reynolds number of the model, so Vm, Lm, nu m, has to be the same as Vp, Lp, nu p. And these two values are, we can get those from a table, right? Because we know that the prototype is going to be running in seawater. And the value for that is going to be 1.26 times 10 to the negative fifth feet squared per second. And the model is going to be run in standard air. And that value is 1.57 times 10 to the negative fourth feet squared per second. All right. So rearranging our variables a little bit, we can write this as Vm equals to nu m over nu p multiplied by Lp over Lm times Vp. And we know we can give a ratio of these two, right? And then the ratio of this factor here, we can just get from this here. So we know that, we'll write it down here. So Vm is going to be equal to 1.57 times 10 to the negative fourth over 1.26 times 10 to the negative fifth multiplied by Lp times, and our model is 1/15th Lp. If you want to, you can just solve for this ratio up here, but just for sake of example, I went ahead and plugged that in there. And Vp. All right, so we already know what the velocity of the model has to be, right? Because that's what we're testing it at. So 180. And I'll just rewrite these numbers. And then these two cancel out. Flip that up times 15. And then Vp is what we're solving for, right? How fast is the prototype moving for similarity with what we've tested in the lab, right? Move this up a little bit. And then you just plug into your calculator and you'll get Vp as 0.963 feet per second. And there's your answer. So for Reynolds number similarity in this scenario here that we have, where we're working with a model and running it through a wind tunnel, if our prototype is running this fast through seawater, they're going to have the same Reynolds number relationship. All right, so that's the first problem we're going to go through. We're going to see something similar for the second problem, so stick around for that one.